Hello everybody, good morning to my dear friends, and I welcome to my presentation on the topic of engineering of bulk and nanomaterials for smart sensing of gas, light and food freshness. Just about the statutory warning of gas concentration, what is present in the environment, that is gas concentration above TLV is harmful to living beings. This is the introductory part of about the gas sensors. So what is the environment? The environment is the imperceptible relationship between the nature and the human mind. And when the condition exists when the atmosphere contains the concentration of pollutants, those produce objectionable effects that we call as pollution. Friends, environment is related not to us, but it is related to the human and its mind. If there is no mind, there is no environment. See, this is a Tolstoy's man. He is breaking the earth as a whole. That it is rapidly growing and advancing technology, grabbing and robbing the beautiful nature speedily and thoughtlessly. So, what is the result of this grabbing and robbing the beautiful nature? That explosive growth of environmental pollution that we are facing, the many problems such as the global warming is the major problem that we are facing nowadays. So here we come across many gases which are present in the environment that we must detect them. So we categorize the hazardous and toxic gases into three types. First is combustible gases. We come across the explosion of fire hazard from such gases. Then toxic gases and oxygen displacing gases. So let us see the combustible gases. So for combustible gases, there is one term that is lower explosive limit. When the gas molecules in the specified limit, if they exist in the environment, then it is harmful to the environment and living beings. So 100% LEL, lower explosive limit of methane, means 5% by volume. Here you see from 0 to 5%, it is just about to lean for combustion, and that is called as lower explosive limit, that is 100% LEL. If the gas leaks above 5% in the environment, then it supports to combustion. Then from up to above 5%, the gas is supports the explosion and combustion. Above 15% by volume, the gas has crossed the upper explosive limit, that is too rich for combustion. Same the case is found in the case of pentane. Pentane has 1.5 volume percent as a 100% LEL and 7.8% as 100% of upper explosive limit UEL. Second one is toxic gases. Hazard to human health and life safety. That toxic gas can be measured in ppm, means it does not affect if it leaks by some volume percent below threshold limit value, which is measured in terms of parts per million, that is ppm. 1 volume percent of the toxic gases equals 10,000 ppm, or 1 ppm is equal to 0.001% by volume. So this is just about the concentration of the gas which leaks in the environment. Here we see the carbon monoxide hazard. So carbon monoxide is one of the most hazardous gases. Hemoglobin has about 210 times more affinity for carbon monoxide than for oxygen. Means hemoglobin just combines with carbon monoxide so that it forms the compound of carboxyhemoglobin, and oxygen is replaced instead of here carbon monoxide. So it reduces the ability of hemoglobin to carry oxygen to the body tissues. Means we lost the oxygen from our body, and therefore many problems such as mental performance, hearing ability, night vision reduction, time discrimination ability, headache, dizziness, and so many problems we are facing for the carbon monoxide hazards. Then if 100% ppm, 100 ppm of carbon monoxide is leaked in the environment, then fatigue and feeling of being tired. Above 400 ppm, headache within 1 and 2 hours. So dizziness, nausea, headache. Few times, if it is leaked above 3200 ppm, then death may occur within 30 minutes. So this must be avoided. Such type of gases must be detected. So what is the general safety order for carbon monoxide? The permissible exposure limit is in time weighted average, that is 50 ppm for 8-hour exposure. It means that within 8 hours, if 50 ppm carbon monoxide is exposed on a human, then it can be tolerated. But if it is exposed above 50 ppm, then it cannot be tolerated by the human. Short-term exposure limit is 200 ppm for 15 minutes per 8 hours. Means per 8 hours, if 15 minutes exposure of 200 ppm happens, then it is tolerable. Otherwise, it is dangerous to human. Then next one is chlorine hazard. Chlorine hazard, like this carbon monoxide, chlorine is also hazardous to the living beings. Water purification, sanitation of industrial waste, swimming pools, bleaching of pulp and textiles, manufacture of various chemical compounds, and so many things. When that happens together, that means when chlorine gas comes in contact with the moisture, then one hazardous chemical forms, that is called a dioxin, and it may occur death if it is exposed 100 ppm for a few breaths. Then its permissible exposure limit is 0.5 ppm for maximum 8 hours. Its short-term exposure limit is 1 ppm for 15 minutes per hour. Then hydrogen sulfide. Likewise, hydrogen sulfide 1 ppm. It is also produces the irritation of respiratory tract and odor detected. Above 10 ppm, it is allowable for 8 hours exposure, and above it is not tolerable. So its permissible exposure limit is 10 ppm for maximum 8 hours. Likewise, ammonia 2 ppm, 40 ppm, and many. If the ammonia is leaked in the environment by any mistake or by industries, then many side effects the human can occur. Its permissible exposure limit is 25 ppm and short-term exposure limit is 35 ppm for 15 minutes per 8 hours. Similarly, gases containing sulfur, means sulfur oxide, dioxide, and sulfur trioxide, we may find difficult breathing, may strain the victim's heart, bronchitis and lung cancer. It destroys plant cells, and many more hazardous effects we come across. Likewise, ethanol is also it is hazardous to the living beings. Pure ethanol is called as absolute alcohol. Ethanol is used for beverages, scientific and industrial purposes. Though it is hypnotic gas, it depresses the activity of upper brain, even though it gives the illusion of being a stimulant. It is a toxic like methanol, and abuse of ethanol, methanol, or any other alcohol is a major drug problem in most countries. This is the carbon dioxide hazards. So, alone carbon dioxide 50% is responsible for the global warming. Then oxygen deficiency hazardous. So that is normal oxygen concentration in air is 20.9% by volume. And if this magnitude or by this, if this volume gets decreased or increased, many more effects we come across. Breathing air required above 19.5% and below 23.5% oxygen content in air. So let us see what is sensor. Sensor is the electronic device which responds to physical quantities, whatever the quantities may be, whether it may be gas concentration, whether it may be temperature, whether it may be pressure, or whether it may be displacement. So physical quantities, they are converted into electrical variations. That device is called as sensor. It is also defined as any device that converts a signal from one form to another form. And gas sensor is a type of chemical sensor which senses the odor of the gas. Just as E knows that it senses the odor of the gas and gas concentration. Gas sensor measures the concentration of the gas in its vicinity, means exposure. So sensor is the input device of any system. If we consider the public address system, the input device is microphone, that is called as sensor. And actuator is the output device actually in the system. And in the public address system, loudspeaker is the output device. So it is called as actuator. And the signal transformation from input unit to output unit is called as transduction. And the whole system is called as transducer. So here there are number of types of sensors are there. So basically the two types, chemical sensors and physical sensors, we come across the two types of chemical sensors are gas sensor and humidity sensor. And for physical sensors, we find the optical sensor in which the light rays or wavelength or characteristics of light are measured. In mechanical sensor, pressure can be measured. In magnetic sensor, magnetic field, magnetic flux, they are measured. Temperature and electrical sensors. These sensors are the physical sensors. So what is the need of these sensors? Or we come across few most cruelest episodes that methyl isocyanate leakage. Gas is leaked out in the India on December 2, 1984 at Union Carbide plant in Bhopal. So if we have well-developed gas sensor was there, so we can avoid such horrifying or disastrous events. So next one is horrifying explosion of gas cracker plant on November 5th, 1990 at Nagothana in Maharashtra, India. Number of explosion accidents of cooking gas happens in all the kitchens all over the world. The top of the wonders of the world, India's pride, Taj Mahal, is blackening away due to industrial and vehicular pollution. If we minimize such the emission of gas effects, to minimize the health hazards, to avoid the hazards of global warming and to avoid the cruelest episodes, it is necessary to detect and control the pollutants in the environment in the form of gas or moisture. So various nanomaterials are used in the sensing. So here we have zero dimension nanoparticle, means nanoparticles having size 1 to 100 nanometer. Then one dimension means one dimension of this system is bulk, means in terms of microns. However, the two direct dimensions are reduced to nano size. That is called as one dimension nano rods or nano wires. This is the nano wire and this is the nano rod. Then here we come across 2D materials, means any two dimensions are bulk and one dimension is reduced to the nano size. So this is 2D and this is the bulk 3D material. So here we find the single wall nanotube, rope single wall nanotube, nanorod, multi-wall nanotube, nanoclay. These find the applications in the sensors to detect the gaseous species or light or food freshness detection. Why do nanomaterials give crucial response in gas sensing? So see here, this is the nanomaterial. When before exposure of the gas, see the oxygen species get absorbed on the surface, and that oxygen species, they capture the electrons from the conduction band, and the potential barrier or the depletion region forms there. So that depletion region or potential barrier can be described by delta in this figure. Then again on the other side, there is one again potential barrier happens. So this potential barrier on this side and on this side, this reduces the conduction channel of the electrons. The total diameter of this particle is from this one to this one, means it is designated by capital D. So the channel available to conduct the electrons is capital D minus 2 delta, that is LC. So this is the blocked conduction channel due to potential barrier in air ambient. And this is the broadest conduction channel on exposure of target gas. So what happens when the target gas is exposed on the material, on the surface of the material, then the oxygen gets combined with the hydrogen, liberating the water molecule, and the hold or captured electron by oxygen that is trapping behind in the material. This reduces the conduction channel, this reduces the potential barrier and widens the conduction channel to carry the electrons throughout the material, and that's why its conductivity increases. So this is just the basic mechanism of the material in the gas sensing. That's why the nanomaterials give the crucial response to gas sensing. So this is just about the gas sensor circuit. This is the block diagram, or this is just the block diagram of the static gas sensing system. Here we find the DC regulated power supply. It is connected to the sensor in the simple circuit, that is in Ohm's law. Then the gas is exposed on the sensor. The gas is exposed on the sensor through this gas exposure unit. Then the heater is installed just below the sensor. Then the output signal is amplified and synchronized by this digital system. Then it is converted into analog to digital converter is used to convert the analog signal into digital signal. This is the digital signal processor and this is the monitor. So this is just about the basic circuit of the gas sensor circuit. Few gas sensors are already prepared by Figaro Engineering Incorporation, Eco Sensors Incorporation, International Sensor Technology, and Sierra Monitors. Friends, these are the four world leading companies. They are fabricating the gas sensors. So we have studied few models of these sensors. Here TGS 824, TGS 825. So like these sensors, they are developed by Figaro Engineering Incorporation. Means TGS means Taguchi gas sensor, and Sierra Monitors have fabricated CM 99447, and the another companies, they are providing GD 801 like this, LPM 2610. So here TGS 824 this sensor is the ammonia sensor. Its detection limit is from 30 ppm to 300 ppm. It means that if the gas is leaked, the ammonia gas is leaked in the environment above 30 ppm, then and then this TGS-824 sensor gets operated and it gives the signal. However, we have 25 ppm is the threshold limit value of the ammonia gas, and if 25 ppm gas is leaked and it is checked, then we can avoid the hazardous effects. But here TGS-824 have the limitation 30 ppm. In the likewise TGS-826, it is again ammonia sensor. TGS-2610 is the LPG sensor. It operates at 500 ppm minimum, but its TLV to fire is 100 ppm. So the LPG must be detected before 100 ppm concentration in the environment. So this is my main aim to develop these sensors. Many techniques are available to fabricate the gas sensors. They are thin films, thick films, and pellets. Here, out of which we prefer thick film technology because it is low cost, it has high porosity, because as the gas sensor is the surface phenomena, so we must need the porosity on the surface of the film, which we can manipulate by using the thick film technology. Then there is a good control over thickness of the film. We can fabricate the films of different thicknesses, and the easier mass production is there. So how many, which materials are used during this study? They are ZNO, zinc oxide, zirconium oxide, molybdenum oxide, tin oxide, titanium oxide, and so many. To modify such base materials, some misfits are used, such as alumina, L23, chromium, Cr23, Cu, Fe23, and number of oxide materials are used as misfits in the base materials, so that we can modify the base materials and get the proper results for gas sensing. Here we have three modifying techniques, that is calcination at the higher temperature in the muffle furnace, then dipping our film, dipping the film of pure material in the misfits solution, and the doping means the misfits can be added mechanically with a very minute quantity in the base materials. So these are the low cost techniques again to modify the gas sensors or to modify the sensing performance of the different materials. Here first is the modifying technique, that is calcination. If the material is calcined at high temperature, then if we took the example of ZNO, after calcined at higher temperature, means above 500 degrees Celsius temperature, so it liberates its oxygen. Oxygen is removed and the material gets oxygen deficient. So actually the theoretical stoichiometric proportion of zinc and oxygen in ZNO are 18.34 and 19.66. This is theoretical, but practically what we have synthesized the material and it is analyzed after EDS analysis, then we find that the zinc is excess, means it is 91.95, and oxygen instead of 19.66 it appears as only 8.05. It means that this material is oxygen deficient, and as it is oxygen deficient, so oxygen that captures the electrons, they are less, means less number of electrons are captured by the oxygen species, and so number of free electrons are available to carry the current in the material, and so this material becomes N-type. That's why ZNO with more oxygen deficient show the more N-typeness of the material. So this is just about the potential energy diagram for the ZNO. So here zinc Zn2 plus O2 minus, Zn2 plus O2 minus. This is the periodic arrangement. But if we liberate one oxygen, then Zn2 plus and Zn2 plus form this type of structure. It modifies the potential energy diagram, and so this N-type semiconductor gets developed. This is this missing one oxygen atom, that is donor level, and in case of CuO, one copper gets evaporated, and here O2 minus forms this type of shape. So this is P-type semiconductor. Here, this is just the picture of dipping and doping techniques. So this is the energy dispersion analysis by X-rays of the material which have been doped by copper in ZNO. So here also we find that the materials are having the less oxygen atoms, and copper is added like this copper oxide. For 2 minutes dipping there is 0.09%. Then for 5 minute dipping it is 0.41, 15 minutes it is 0.51, and for 30 minutes it is 0.42. So in this way we can introduce the copper oxide atoms in the zinc oxide atoms by using dipping technique, doping technique. Thus modifying technique is third one is doping. So here doping means adding one solution in another and forming the compound of the different materials. So this is just about the material synthesis. Here material synthesis has been done in our laboratory by using the microwave aided ultrasonication technique. Dear friends, we have many more techniques available to synthesize the nanomaterials, but in our laboratory we are using the low cost technique, and here this is this type ultrasonicator. So it has the power of 800 wattage, and this is the rod having the disc situated at the tip, and its frequency is 40 kilohertz. So this is the ultrasonic cleaner. So it cleans having the frequency of 24 kilohertz. This is the assembly of the actual reaction what happens on the magnetic stirrer with hot plate, and this is the microwave oven. So here microwave assisted or aided ultrasonication technique is used to fabricate the nanomaterials. So the root of material synthesis is aqueous alcohol solution. First we prepared by distilled water and propylene glycol in 1:1%. Then zirconium oxychloride is added. If we have to find the film of zirconium, then zirconium oxychloride in 0.1 molar is added to this aqueous alcohol solution. Then dropwise ammonia is added in the solution, which is held on the magnetic stirrer with hot plate. Then ammonia is added till pH becomes more than 8 or more than 8. That's why we got the particular size of the material. If we perfectly manipulate the pH of the material, concentration of the solutions, then we can get different forms of materials, different forms of nanomaterials. They are nanorods, nanoplates, nanoflowers, nanopetals, nanorobes, and even nanoparticles. So we can achieve the different shapes of the nanoparticles with different sizes. So this is just about the engineering of nanomaterials synthesis. Then this PPT was washed with distilled water, followed by ultrasonication and micro irradiation. Then we get the nanomaterials of a particular shape and size. So once nanomaterial has been prepared in terms of the dry powder, then the thixotropic paste may be formed by following this route, the functional material, and if ethyl cellulose, organic solvents, they are added in functional materials, followed by screen printing and drying technique, we can get the thick film. So this is the screen printing setup. Here, this is a screen. The screen is held with this clamp, and here the the stencils are present like this, and just below the substrates are kept. So once we press this screen by squeegee like this, this is the screen printing mechanism. The squeegee can get material through these channels of the screen opening. Then the material get passed through the screen opening, and like this, the sensor materials gets printed on substrate. This is the sensor material. These black points are the sensor elements of size 4 mm to 9 mm. This is the static gas sensing system, block diagram of static gas sensing system. We have shown earlier one gas. So here, this is the glass dome. This maintains the environment. This is sensor. The sensor is fitted just above the heater, which is placed on the base plate. Then in the base plate and heater, there is one insulating slab upon which the heater gets placed. The thermocouple is mounted near about the sensor to measure the temperature of the sensor, and this sensor is connected to picoammeter and power supply, so that whatever the change in current is observed, we can observe it on the picoammeter. Then here the another special unit is their gas inject unit. The gas can be passed through this syringe into this pipe, and that is exposed on this sensor. So this is just about the block diagram, and this is the actual photograph of the static gas sensing system. This is actual photograph. So here, this is picometer, power supply. This is the dimmer stand to control heater. This base plate heater. This sensor is fitted inside this glass dome. This is the glass dome, and we can measure the output with the in terms of the current in the picometer or the resistance by taking the ratio of voltage and current. So volume of the gas can be controlled manually, or otherwise it can be controlled by flow meter. So manually, how can be it is achieved? That chart is given here. We have the glass dome of volume 15 liter So if the gas exposed on the film is 1.5 ml, then it is 100 ppm gas concentration. If it is 3.0, then it is 200 ppm. By calculating the volume of the gas in ppm is equal to injected volume of gas upon volume of glass dome, which is 15 liter, multiplied by 10 raised to 6, so that we can convert this volume of the gas in ppm. We have important measures of gas sensing performance. They are the gas response. So before exposing the gas, we measure the current, and after exposure of the gas, we measure the current by taking the ratio of the gas currents in the gaseous medium and in the air medium. By taking this ratio, we can get the gas response. It is, ideally speaking, the gas response should be high for any material. For selectivity should be also very high. Even though gas response is medium or some factor less, but selectivity must be high, because the gas sensor should give the response to only a selective gas, either of one and not more gases. So selectivity is the ability of a sensor to respond to a single gas in a mixture of number of gases. So next one is response time. The time to which the gas exhibits the response, more response, or up to 90% response, that is called as response time. And ideally speaking, that response time should be in terms of few seconds and not for few minutes. Then recovery time. Once the gas is exposed on the material or the sensor, then its chemical constitution or composition get changed. But after firing again, that film should come to its original chemical status without any processing. That is called as recovery, and that time should also be very low. Means, ideally speaking, the recovery time must be a few seconds and not few minutes. Operating temperature. Sometimes many gas sensors exhibit the gas response to the temperature range from room temperature to higher temperature, that is 300, 350, like this. So at what temperature the sensor responds to a particular gas with maximum amount, that is called as operating temperature. So here few sensors are room temperature sensors are developed in our laboratory. They are ammonia, chlorine, H2S, LPG, and hydrogen. And few sensors operable at higher temperature, they also developed in our laboratory, that is ammonia, LPG, hydrogen, and ethanol. So here we have some scanning electron microscopic micrographs for 0D materials. So these are the nanoparticles of the size from 5 nanometers to 20 nanometers and even more. So these pictures show the nanoparticles, that is 0D materials. Then here nanorods, that is 1D materials. You can see it is a very strange that materials or the particles can be arranged in a line forming the nanorods. See, this is the nanorod, and here nanorod formation process is going on. Here also one nanorod gets formed. So here this clearly states the formation of nanorod of the particles. When they are collected, this nanorod is formed already. This is also one nanorod. So number of nanorods get formed from the nanoparticles. This is called as one-dimensional materials. So here also the nanorods, and this is the lump of nanorods. Here again, few nanorods we have synthesized in our laboratory. Nanorobes. It is a very strange event that you see how the nanorobes gets formed. That is, this process is incompleted. If we control this proper way, by proper way, then we can get such pictures during the formation. And if we give some more time, then the nanorobes like this, they get formed in the during the synthesis. So this is also the 1D material. Then nanoflowers and nanopetals of 2D materials. So here, this is the process of nanoflowers formation. Here, that petals get spreaded like this in this picture, and here number of flowers, nanoflowers, they are forming. That is, this is called as the engineering of nanomaterials formation.
Sir, Professor Patil.
Yes, sir.
So could you make a quick summary, because
yes, sir. Yes, sir.
Thank you, sir.
Yes, sir. So here we have two gas sensing mechanisms: adsorption, desorption of oxygen, and heterojunction formation. So before exposure of the gas, oxygen can capture the 2 electrons from the material, and it becomes 2O minus. So these appear on the surface of the sensor, and after exposure, this oxygen liberates the electrons in the material. So this is another mechanism, heterojunctions formation. Before exposure of H2S gas, NSNO2 PCO, that is PN junction, it shows very high resistance. This is the resistive model of the sensor. And once the H2S gas is exposed, so PCO gets converted into conducting CUS and ruptures the NP junction, becomes very low resistance. So here the ammonia sensor is there, IV characteristics, conductivity. Then this here you see ammonia response at pure ZNO at 400 degrees Celsius, it gives response to 17. Fe added ZNO gives response to 96 at lower temperature, that is 350 degrees Celsius, and Fe deep ZNO gives more response, means 2 times response at the same temperature. So this is the weakness of the sensor, that it operates at a very high temperature, that is 350 degrees Celsius and 400 degrees Celsius. So let us work to obtain the room temperature sensor, and we got the room temperature sensor and Cr2O3 ZNO reported as humidity sensor, and that sensor responds to room temperature. So CRD plus ZNO sensor gives the response to room temperature. So this is about the output of this laboratory. Room temperature chlorine sensor we have room temperature H2S sensor, then H2S. This is again the LPG response. LPG is not showing the response at room temperature for these mixed metal oxide materials. Here hydrogen response, ethanol. So our next topic is light detection. Here particle size during the synthesis, the particle size with doping concentration gets here presented. So for 0 weight percent, we have particle size 2.4 nanometers. For 1 weight percent, it is 5 nanometers. At 3 weight percent, it is 5.4. and at 5 weight percent it is 7.03 nanoparticles. So just the particle size depends upon the doping concentration. This is the optical band gap. Here for TI 1%, 3% and 5%, we have observed the energy band gaps. They are 2.36 electron volt, 2.30 electron volt and 2.21 electron volt for 1 weight percent, 3 weight percent and 5 weight percent respectively. Here we have one very advanced response to green light. So here green light sensor, we got the material response. We have synthesized the thin films, and that thin film of Zn, magnesium, then tellurium, and like these materials, cadmium based, tellurium, zinc. So these materials give the response to green light more, as shown in these figures. This is the time-based green light detection, and this is the photoluminescence measurement. So green light detection of the various materials is shown in this picture, and thermoelectric power measurement is also present like this. EMF, thermo EMF versus the change in temperature. Then this is the solar cell, thin film solar cell. Here, this is the platinum plate. This is used for one contact. This is the another contact, which is called as CDS thin film. And in between platinum plate and CDS thin film, one cavity is there in which the electrolytes can be passed by a syringe with force, so that this responds to the solar radiations which are sent through this window. So we have this type of IV characteristics of solar cells, showing many more response to different situations and different solar radiations at different wavelengths. So somewhat innovative work we are doing in our laboratory. We found the temperature notch sensors, food freshness monitor, and disease diagnosis. These are the points for which we are preparing and filing for patents. So we have not disclosed these points in my presentation. So for this, I'm very sorry. If you have any queries, you can ask me or you can mail me. So